proofs of conjectures by Polignac and Hardy-Littlewood. Although we have, for all intensive purposes, proven Polignac's lemma, we will spell it out clearly here. Since gap tuples of 2j, 2, 4, 2, 4, with j even, and 2j, 4, 2, 4, 2, with j odd, will always exist, the ckn will cause all nearby increments of j to exist. It's unstoppable. In previous lectures we showed the count of twin gaps in any iteration is the second minor primordial. Since Sm is a random bag, what we really want to use is the local density, Rf1 at m, divided by the count of the entire set. In 1923, Hardy and Littlewood showed the limit of the twins' frequency times the local expected average tended to a constant of about 4/3. Their counting, however, found half the constant, which they later always multiply by 2. They went on to conjecture. This constant divided by the logarithm was a reasonable forecast for the twins' frequency. But we know there is an e to the gamma scale factor baked in, and we must reconcile this. The resolution is straightforward. Within the S model, the local frequency is exactly what the model predicts, and we should unwind our product by dividing by the local average. While among the primes, we leave the e to the gamma scale factor baked in. That is, the Hardy-Littlewood twin prime conjecture is trivially true in the S model, and so trivially true among the primes. The differences between models is the e to the gamma scale factor, and we can readily prove many more such conjectures using the primordial algebra inherent in the S model. However, they also went on to make a more general conjecture. They gave a heuristic argument that in general, the local count of the set of all gaps that summed to j, with j being any positive integer, occurred at the boosted rate of the following product: the first occurrence of prime factors greater than or equal to 2, where it is assumed in the product that 2 minus 2 is 1. These boosts are exact in the S model because the same argument they used heuristically is true at the appropriate iteration. Because of these boosts, and because each individual gap count of size 2j is the sum of all substrings, minus those of length 2, 3, and so on, to some maximum span, the first term of every gap-type count equation is Rj times our second minor primordial. This leads to a simplification of our calculus of finding gap formulas. For example, it instantly predicts the exact count of twins and cousins. The appropriate range for first occurrence is when j is near r prime times its log, for j being any positive integer. Due to the lumpy character of the distribution, It actually occurs somewhat before this. Importantly, this gives us the first constant from our unknown set of algebraic constants of count k that describe the formula for gap 2j. So we only need to solve a k-1 by k-1 matrix, and given the explosive growth of the set sizes, it is a surprisingly powerful addition to the S-model probe kit. For example, to find the final form of sexes, we only needed to find the count of the first atomic pairs, 4, 2, and 2, 4. This leads to another trivial conclusion we can draw. The last, or deepest term in the series, is atomic, and only this last term is atomic. Given the enormous value of predicting a single term, we suggest a new avenue of research. Finding the generalized constants for pairs. We know this is not trivial, but there is a hint in the study of the HL boost factor. Remembering our boost factor formula, it is immediately apparent that a boost is actually a resonance that fits every SM, because its local ratio divides every SM above an appropriate M. Asking the same of pairs suggests something akin to the following products. That is, pairs whose individual members and their whole must share a resonance within the second minor primorial, the main driving force of prime gap distributions. We probed this and immediately found the following exceptions. Given a gap pair A, B, if both members are divisible by 6, the boost factor is further boosted by 2. That is, we conjecture the first term of every pair's formula for the pair A, B has the constant of multiplication of the product of our individual products, suitably boosted by the mod 6 exception. The exceptions tell us we are missing other factors that are conditioned on the exceptions. That is, we found an exception and a rule, but do not know why it is true. A reliable solution gives us one more count for free, reducing our constant solving problem to solving a k-2 by k-2 matrix. In other words, it gives an extra deeper probe into an otherwise inaccessible space, the exponentially exploding S-model. In the next video, we will use a combined results to produce two different proofs of Riemann's hypothesis. We can say without doubt the results are far more interesting than the proofs. As for the proofs, all we can say is they are easy, and we were very lucky. For more information, please see the next lecture, or Google multiplication modulo n along the primorials, with its differences and variations, applied to the study of the distributions of prime number gaps.